All right, section 7.3, central limit theorem for sample proportions. So let's start with a review of what a sampling distribution is. So keep in mind it's a probability distribution for a statistic, and in this chapter we're interested in p hat. All right, it shows all the possible values of the statistic on the horizontal axes. So I'm going to refer us down to here. So notice that all of the values of p hat, all your values of sample proportions are on the horizontal axes. It's a probability distribution because it gives you the probabilities on the vertical axes. So again, it's listing these potential values of p hat, and the heights of the lines above them are giving you the probability that they occur. All right, so that's our third bullet. It gives you the probability of each possible statistic, and it tells you how often you can expect to see particular values of your estimator. Again, your estimator is p hat. It also gives you important characteristics of the estimator, such as bias and precision. So remember that bias is interested in where the center is, and our hope is that the center is at P. And it also talks about precision, which is another word for spread. So we'll be able to calculate standard deviations for these distributions. All right, and it's used for making inferences about a population. It allows you to generalize the results of a survey, which is from your sample, to a larger group, the population. It's also going to allow you to quantify how far off your estimates are likely to be by calculating the probability that an estimate falls a specified distance from the population value. So in how far away is p hat from your population value, which is p. So again, your estimate is p hat, your population value is p. All right, so number 2, we saw multiple sampling distributions in our previous class. Following is the sampling distribution for p hat when you take random samples of size 4 from a population with 8 students, and you record the proportion of students that consider themselves cat people. So in each of these values on your horizontal axes, your p hat was the proportion of people, or proportion of your sample, that identified as cat people. And keep in mind that in this particular population, we had 8 students, and P, the proportion of the population that preferred cats, there were 2. So P was 25%. So we can see there was no bias here because our center of our sampling distribution was equal to P. All right, so number 3, the following is an approximated sampling distribution for p hat when we take random samples of size 10 from a population with 1,000 students and record the proportion of students that consider themselves cat people. It is an approximated sampling distribution in this case, since it contains the results of a simulation with 10,000 repetitions or samples. So just some information from above. Our sample size was 10. The population size was 1,000 students, and we are going to continue to assume that 25% of the population were cat people. All right, so notice on your vertical axis here it says frequency, so it's telling us how many samples had each particular result. But we could rescale this axis if we wanted to and convert it to relative frequency or probability. So remember that there were 10,000 repetitions. So for instance, 500 out of 10,000 get the right number of zeros there, would give us 5% or 0.05. So again, we could rescale this axis and have probabilities on the vertical axis instead of counts. All right, looking at this a little bit further, this first bar tells us that there were roughly maybe 525 samples. It's an estimate with 0%, or we'll say 0% cat people, or 0 cat people. And there's maybe, we'll say maybe 10 samples with 70% cat people. And keep in mind, 70% cat people meant that 7 out of the 10 people sampled were cat people. And here, 0%, 0 out of the 10 people sampled were cat people. And the last thing I want to point out to you is this horizontal axis is p hat, so these are sample proportions. All the different values of p hat for each particular sample that is collected. All right, number 4, the following is also an approximated sampling distribution for p hat when you take random samples of size 100. So you've got sample sizes of 100 from a population with 1,000 students. So size of the population is still 1,000. And record the proportion of students that consider themselves cat people. So we're going to still assume, like the previous problem, that the proportion of people in the population that prefer cats is 25%. So it's again an approximated sampling distribution since it contains the results of a simulation with 10,000 repetitions or samples. All right, so again, we could rescale this axis here instead of frequency. We could rescale it or recalibrate it so it was expressed as probabilities. So this would be at 0%, 500 out of 10,000 would be 5% or 0.05 rather, 10%, and so on. And so let's take a look. We've got, let's see, 10%. Doesn't have a bar above it, but that would mean that 10% of 100, this would be 10 cat people in the sample. So it doesn't look like they actually got any samples with that few cat people. And down here, 40%, there's a bar above that. That 40% of the sample being cat people would be 40 cat people. 40% of 100 is 40. And again, these values on your horizontal axes are all values of p hat, which is your sample proportion. All right, so let's compare this approximate sampling distribution when n equal to 100 students to the previous sampling distribution when n was 10 students. All right, notice that the center of each approximated sampling distribution is at p equal to 25%, indicating that the sampling methods are unbiased. Again, the difference between p and the center of the distribution, the mean, was 0. All right, the second estimator, n equal to 100, is much more precise than the previous estimator when n was 10. And that's because the sample size is larger. So by sampling more people, we get more information, and we end up with a more precise estimate. So remember that more precise is indicated by less spread on the horizontal axes. Right, so if you look at the second graph, looks like the percentages went from maybe about 11 or 12% up to about maybe 41%. But on the first graph, they went from a low of 0% up to a high of 70%. So again, the second graph had a lot more precision, less spread, smaller distance between the smallest and largest values in there. All right, next, the shape of the second sampling distribution is unimodal and more symmetric. In fact, if you look at the first distribution, there's a little bit more skewness to the right. And lastly, there are so many more possible values for p hat when n equal to 100 that the sampling distribution looks as though it belongs more to a continuous valued random outcome rather than a discrete valued random outcome. So the first one looks, again, if we go back up here, looks more discrete. Here, this one looks like it might be more continuous. There's so many more values of p hat. It's beginning to look like a continuous valued random outcome. All right, number 6, we saw similar results from our simulation in our last group activity. In this group activity, we used an applet to simulate taking random samples of Reese's Pieces and calculating the proportion of orange candies in each sample. And if you are watching this video ahead of time and you haven't done that applet yet, and that's in your group activity, you may want to come back and look at this again later. Right. So first bullet, the estimator p hat was unbiased. Both means were very close to p equal to 0.50 for samples of size 25 candies and samples of size 100 candies. This is true for all sample sizes as long as we take random samples. The precision improved when the sample size increased. That meant the standard error was smaller for samples of size 100. And lastly, the shape of the sampling distribution was more symmetric for the larger sample size. Okay, number 7, we turned to simulations in these previous examples because the number of possible outcomes was too numerous to handle. 2 questions of interest to us today. Question 1, are these approximated sampling distributions similar to the actual sampling distributions? I want to know if the approximated sampling distributions and actual sampling distributions are similar. The answer is yes, since the sampling methods were random and many repetitions were done. Second question, are the results of these simulations predictable? Do we have to do the simulations? The answer is again yes, which means that we don't need to run a simulation to know what the sampling distribution will look like. Instead, a mathematical theorem called the central limit theorem gives us a very good approximation of the sampling distribution. And central limit theorem, or CLT for short, we're going to be studying that and using that for the rest of the semester. And we're going to see its counterpart for means or sample means when we get to chapter 9. All right, so number 8, we're going to be using the version of the central limit theorem that applies to sample proportions. So these are your p hats today. And again, we'll use the version that applies to sample means in chapter 9. So this version can be used when the following conditions have been met. Your first condition is that the sample is collected randomly from the population and observations are independent of each other. Sample can be collected with or without replacement. Keep in mind this condition is really important because it's going to tell you about the center of your distribution. So it's addressing the issue of bias. So keep in mind if your sampling method is biased, you tend to overrepresent or underrepresent a certain segment of the population, then we know that your p hats are probably not going to be close to p. So the center of your distribution is going to be somewhere else. All right, condition number 2, your sample size has to be large enough that the sample expects at least 10 successes, or yeses, and 10 failures, which are nos. And you can check this condition with 2 calculations. All right, your first calculation is that the sample size times p should be at least 10, and your sample size times 1 minus p should be at least 10. And both have to be met. It's not one or the other, both have to be met. Okay, and if p is not known, you do have an option here. So if p is not known, we can replace p with its estimator p hat. And keep in mind that this particular condition has to do with the shape of your sampling distribution. If your sample sizes are not big enough, your shape is not going to be accurate. What the central limit theorem predicts is not going to be accurate. All right, in condition number 3, if the sample is collected without replacement, so here's something specific to without replacement, then the population size n must be at least 10 times bigger than the sample size. So we can check this condition with the following calculation. So this again is our population size, that's capital N, and that should be at least 10 times bigger, so this is greater than or equal to 10 times the sample size. And if you're curious, since the top 2 conditions had an effect on a particular part of your sampling distribution, this one does too. Condition 3, if that's not met, then the central limit theorem may not accurately predict the spread or standard error of your sampling distribution. Okay, so if these conditions are met, then the sampling distribution for p hat has a shape that's approximately normal, has a mean equal to the population proportion p, and has a standard deviation, which remember we're going to call standard error when we talk about sampling distributions, equal to p times 1 minus p hat over n, and then the square root of that. If you don't know p, remember you can do an estimated standard error, and that just relies on substituting your p hat in for p. All right, so an example, the central limit theorem sampling distribution for p hat is approximately normal. So again, we've got that notation. Remember we had this earlier, we said normal, and then we listed the mean and the standard deviation. We are still doing the same thing. We're going to give the shape, that's what the n is for. And then we're going to give the mean, that's the first number in the parentheses. So this is our mean, or the center of the distribution. And then the second thing is your spread, or standard error. So check out your formula sheets and notice that this is given to you. So it's going to remind you that if you're doing a sampling distribution, you're talking about sample proportions, you're being given the shape, the mean, and the spread or standard error. All right, so the shape is normal. We've got our picture down below. The mean should be in the center, should be the balance point. So we know that's going to be centered at P. And we know if we go 1, 2, and 3 standard deviations, or standard errors in this case, to the left and the right, it should bring us roughly to the end of the distribution. So for instance, this first mark to the right of P is going to be P plus 1 standard error. This is going to be P plus 2 standard errors. And this is going to be P plus 3 standard errors. Over here on the left, this is going to be P minus a standard error, P minus 2 standard errors, and P minus 3 standard errors. And then all these numbers on this horizontal axis are all possible values of your sample proportion. So these are all sample proportions, or P hats. All right, so note, this normal model becomes more and more accurate as your sample size increases. So as n gets bigger, the model becomes more accurate. All right, so let's check to see if the central limit theorem would have correctly predicted the sampling distributions from our previous simulations. So simulation number 1. Following is an approximated sampling distribution for p hat. We take simple random samples. And keep in mind, simple random samples tells us that it was done without replacement. So it's going to make checking that third condition really important. So we did simple random samples of size n equal to 10 from a population with 1,000 students. And the population had 25% cat people. We recorded the proportion of students that considered themselves cat people. It's an approximated sampling distribution in this case since it contains the results of a simulation. And the simulation had 10,000 repetitions of samples in it. All right, so our first step is always going to be to check those conditions. So condition number 1, we want to check to see if random samples were used. Okay, and that we can say yes because they told us that right here. And we want to also make sure that the observations are independent. So in other words, if we pick one person out and they say they're a cat person, that's not going to have any bearing or influence on the next person we pull out of the population for our sample. All right, our second condition, we want to check to see if our sample size is large enough. So we need to check 2 calculations, n times p, see if it's bigger than 10, and n times 1 minus p. And remember, both of these, again, have to be met. So if we take our sample size of 10 times 0.25, we get 2.5. And if we do 10 times 1 minus 0.25, we get 7.5. All right, so notice here we would have to say no, the sample size is not large enough. Okay, and in most cases this is where we would stop and say we can't use the central limit theorem. Okay, but we're going to continue on just to see what happens if we incorrectly use it. All right, so let's use the third condition, or check that first. All right, so we want to check, since we did simple random sampling, which is without replacement, we need to check to see if our population is at least 10 times bigger than our sample. So is n 10 times greater than lowercase n? So our population had, let's see, 1,000 students, and that's bigger than 10 times our sample size of 10. So 1,000 is greater than or equal to 100. So we can say yes for this one. And while I'm here, I should go back and say this one was also yes. All right, so can we use the central limit theorem? We would have to say no. Again, condition 2 was not met. All right, again, we're going to continue to use it just so you can see what would happen. But condition 2 is the problem here. All right, so down below, we have the results of our simulation. What we're going to do is draw the model that the central limit theorem would predict. So it tells us that we would have a normal distribution. Our sampling distribution for p hat should be normal, should be centered at p, which was 0.25, and should have a standard error equal to 0.25 times 1 minus 0.25 over, what was our sample size, was 10. So this is approximately normal, center at 0.25, and a standard error of about 0.1369. And that comma is just to separate the two numbers on our list. So our central limit theorem's model, keep in mind this is the model. Over here on the left, these are actual results from a simulation. And what we're trying to do is see if the model would have predicted what happened with our simulation. All right, so the model says that 0.25 should be in the middle. We have 1, 2, and 3 standard errors to the right, and 1, 2, 3 standard errors to the left. You can fill in some more values. I'm going to press pause and do that. Okay, so filling in those numbers, I took P, 0.25, and I subtracted 1 standard error to get this number. Subtracted 2 standard errors, I added a standard error for each of these, and added 2 standard errors here, added 3 standard errors here. Subtracted a standard error from the mean to get this, 2 standard errors to get that, and 3 standard errors to get that. So again, the question is, if we superimpose this model over here on the left, would it work? And we would see that it probably doesn't match. It looks like it might do something more like this. And that means the model does not fit. And again, that's because of condition number 2. Remember, condition number 2 was about shape. The normal model is, or the central limit theorem's model is normal. It's unimodal and symmetric. If we look, our simulated results were skewed to the right, so it didn't accurately predict the shape. All right, so the last question, does the central limit theorem accurately predict the results of the simulation? We're going to have to say no. All right, let's do a second one, and hopefully this one will give us an example where it does work. All right, so in simulation number 2, the following is an approximated sampling distribution for p hat. When we take random samples, or simple random samples, so we're doing without replacement again, of size n equal to 100 from a population with 1,000 students. And again, p is equal to 25%. We also recorded the proportion of students that consider themselves CAT people. So it is again an approximated sampling distribution, since it contains the results of a simulation with 10,000 repetitions or samples. So and here's our simulated results down here. All right, so to see if the central limit theorem model would have predicted this, let's check our conditions again. So random sample, we can check that one off because it told us that above. So random samples has been met. And are the observations independent of each other? And that also can be met, that simple random samples. We can assume that one person's response as to whether they prefer cats or dogs is not going to have any bearing on another person's response. I'm going to put a check mark there. All right, our second condition has to do with sample size. And again, we have 2 calculations we have to do. So we're looking at n times p and checking to see if it's greater than 10. N times 1 minus p, we want to see if that's bigger than 10 as well, or equal to 10. So we've got 100 as our sample size, times 0.25 is 25, and 100 times 1 minus 0.25 is 75. So this one we can say yes, our sample size is big enough. All right, and then our last condition, because we're dealing with simple random samples, which means it's without replacement, and check to see if our population is at least 10 times our sample size. So our population was 1,000 students. Is that bigger than 10 times our sample size of 100? In this case, 1,000 is the same as 1,000. So it's a good thing there's that equal to sign in here. So population size has to be at least 10 times the sample. So this has been met. We can say yes and check that one off. All right, so can we use the central limit theorem? Yes, we can. And what we should see down here is that the model is a good fit. All right, so let's see what our model is. Central limit theorem says it should be normal, should be centered at p, which is 0.25, and should have a standard error of 0.25 times 1 minus 0.25 over, what was our sample size, 100. Right, so if we do that calculation out, we get a normal distribution centered at 0.25. and a standard error of 0.0433. All right, so the n in that notation tells us the shape. First number inside the parentheses tells us the center. And then the second number tells us the standard error, which is just, again, another name for standard deviation. So I'm just going to fill in, I'm going to use 0.04 just to make things a little easier. So if I add one standard error, add two standard errors, add three standard errors. If I go back, one standard error, two standard errors, three standard errors. Again, keep in mind, on your horizontal axes here, these are all sample proportions or possible values of p hat. All right, so is that a good fit for the model? Well, if we could pick that up and put it on top of this, our simulated results, we would find that it is a good fit. An easy way to check is to check the center. Center's at 25%, that matches. Check the shape. This is definitely unimodal and symmetric, so shape's all set. And then check the spread. Let's check where it starts and stops. So we're expecting to go from 0.13 to 0.37. This is maybe about 12%, so pretty close to 13%. And looks like maybe it ends right about here, right about 40%. So pretty close. Right, so I would say here the central limit theorem did accurately predict the results of this simulation. And again, that means here that the model fit, or the model fits our simulated results. And the big news here is that means we don't have to run simulations anymore. We're going to be able instead just use the central limit theorem to build these models. Okay, so some observations. In the first case, the sample size was too small. Remember, that second condition wasn't met, and it was too small for the central limit theorem to apply. So in this case, the simulated sampling distribution does not look normal. It's not symmetric. It is right skewed and has large gaps between values. The simulated sampling distribution is shown below. This diagram is also on page 318 of your textbook. And keep in mind, it did predict the mean, but the shape, again, was not correct. This is skewed right, and the model predicted it to be normal, or mound-shaped. Right, in the second case, all three conditions are met, and the central limit theorem applied. Simulated sampling distribution looks very close to the normal model predicted by the central limit theorem. Diagram below shows the simulated sampling distribution with the normal model superimposed. And this diagram is again shown on page 318 of your textbook if you want to take a closer look at it. So if you look, again, here's the model, that red line drawn in, and it's a very good fit for the histogram that's underneath it. So note the central limit theorem correctly predicted the mean of both sampling distributions, but not the shape. And that was condition number 2 that hadn't been met in the first case. Also, the sampling distribution for sample size n equal to 100 had more precision than the sampling distribution for sample size n equal to 10. In fact, if you take a closer look up here and here, notice that the axes both go from 0% to 80%. So precision's a little easier to see because we can see that the top graph started at 0%, not quite lined up perfectly, I guess, and ended at 80%. Oops, actually the last value in there, get rid of that last line. Oops. The last value in there was around 70%, it looks like, not 80. So we can see a much more precise distribution in the second one because this only goes from about 10% to about 40% instead of 0 to 70%. So another way to think about precision is that your standard error when n was 10 was smaller. Oh, no, I have that backwards. Was bigger than when your standard error, the standard error you got when n was 100. So you had 0.1369 when your sample sizes were 10, and that's bigger than the 0.0433 that you had when your sample sizes were 100. All right, let's take a look at just one more simulation. So following is an approximated sampling distribution for p hat when you take random samples of size 100 from a large population of Reese's Pieces. and your population has 50% orange candies. So we're going to record the proportion of orange candies in each sample. So it is again an approximated sampling distribution, since it contains the results of a simulation. And this simulation had 10,000 repetitions or samples. All right, so again, keep in mind that random samples doesn't really say with or without replacement. Information's not given, so we have to check the without replacement condition. All right, so our first condition is still the same. I'm going to check and see if they were told that they were random samples, and we were. It's right here. And we need to check to see whether we can assume that observations are independent of each other. And one Reese's Pieces candy's color is independent of the other, so I think we can assume that the first condition has been met. All right, our second condition has to do with sample size. So we want to see if that's big enough. So we're going to do those two calculations, n times p, see if it's bigger than or equal to 10, n times 1 minus p, and again, see if that's bigger than or equal to 10. So our sample size is 100, times that by 0.5, and we get 50. And 100 times 1 minus 0.5 is also 50. So we can say, yes, our sample size is big enough. And we can check off that condition. And then our third condition, again, we don't know. It didn't say simple random samples, so we don't really know for sure if it was with or without replacement. So we're going to check that third condition and see if our population size is at least 10 times bigger than our sample. So our population size, we don't have that. But we do have our sample size. So our sample size was 100. So the question is, are there at least 1,000 Reese's Pieces in the population? And I think that is safe to assume. So most likely more than 1,000 Reese's Pieces. In the population. If you imagine all the Reese's Pieces that have been produced, there's definitely more than 1,000. All right, so we can use the central limit theorem. All right, so moving down here, we want to see what our model would be. So our central limit theorem tells us the sampling distribution for p hat is going to be normal, centered at p, which is 50%, and a standard error equal to 0.5 times 1 minus 0.5. over our sample size, and we've got to take the square root of that. So it's going to be approximately normal, centered at 0.5, and a spread of 0.05. So here's the model predicted by the central limit theorem. Again, n gives you the shape. First number in your parentheses gives you the center. Second number gives you a way to mark your horizontal axes and get a better idea of how spread out everything is. So 1 standard error above, 2 standard errors, 3 standard errors, and then 1 standard deviation below, or 1 standard error below, 2 standard errors below, 3 standard errors below. And again, on your horizontal axes are all these possible values of your sample proportion. So what you might get for the percentage of orange in any particular sample you collect. And again, this is the model. All right, so let's see, how did we do? So let's check the center. Model predicts the center to be at 0.5. Looks like it did a good job of predicting the middle. That looks like about where our peak is in this distribution. Looks like it goes from 0.35 to 0.65 according to our model. So I would say it looks like it starts roughly at 0.35 and ends right around 0.65. There might be 1 or 2 below or above that. And then the shape is also accurate. We've got a normal mound-shaped symmetrical distribution here. All right, so the central limit theorem accurately predict the results of the simulation. We're going to say yes. All right, so 12, a reminder. Probability tells us how often an event will occur if we repeat an experiment an infinite number of times. This means that the sampling distribution for p hat gives us the probabilities of where our sample proportions will fall. That is, it tells us how often we would see particular values of p hat if we could repeat our survey infinitely many times. It can also tell us how likely it is that we will find a p hat within a given interval, how likely it is that we will find a p hat greater than a particular value, how likely it is that we will find a p hat less than a particular value. And so let's take a look at how the central limit theorem can be used to answer these types of questions. How likely is it that our p-hat will be within a given interval? So let's return to our population of 1,000 people with p equal to 25% cat people. We've already checked that the conditions of the central limit theorem have been met when the sample size is 100. So we can skip that first step and move on to number 2, or the first bullet. We're going to draw the normal model for the sampling distribution for p-hat. So we want to make sure we include the mean, the center of our distribution, as well as 1, 2, 3 standard errors above and below. And we want a title for our horizontal axes. So we know that the sampling distribution of p-hat is normal. It should be centered at the population proportion of 0.25 and should have a spread equal to 0.25 times 1 minus 0.25 over our sample size of 100. So this is approximately normal of 0.25 and a spread of 0.0433. All right, so I've got my n, the shape is normal. The center should be at 0.25. And I'm going to round to 0.04 just to make things easier for the standard error. So this should be 0.29, 0.33, and 0.37. And coming down, we got 0.21, 0.17, 0.13. The only thing missing is our axes title. So we want to say that these are sample proportions. If we want to be more specific, we can. We can say it's the proportion of cat people in our sample. All right, so next up, we're going to use this normal model to find the following probabilities. First one, we're going to look at the probability that the proportion of cat people in our sample is greater than 26%. So this is asking, what's the probability that p-hat is greater than 26%? So we need to standardize this because we want to be able to use the standard normal distribution. So we need a z-score. So what's the proportion of z-scores greater than? Well, 0.26 minus the center of our distribution divided by the spread of our distribution, which in this case is our standard error, gives us this statement. What's the proportion of z-scores greater than 0.23? And if you check your table, and keep in mind that since we're doing a greater than, we're going to have to do some subtraction. We're going to find that that area or probability is equal to 1 minus 0.5910. And that's the same as 0.4090. And I would encourage you to press pause, grab that table for your standard normal probabilities, and double check that. And the second one, we want the probability that you get a sample proportion less than 20%. So that's the probability you get a z-score less than 0.2 minus 0.25 over 0.0433. Which if we simplify is the proportion of z-scores less than negative 1.15, and that is equal to, again, check your tables, but you should get an area of 0.1251. And then the last one. We don't have either of these values standardized, so I'm going to do that first. Call this the first z-score. And notice I'm putting these in decimal form because our mean and our standard error are in decimal form. That first proportion corresponds to a z-score of negative 2.31. Our second z-score, so I'll put a 2 there for the second one, it's going to be 0.3 minus 0.25 divided by 0.0433, and that's a z-score of 1.15. So now we've got the statement that our z-score should be between negative 2.31 and 1.15. And again, I'll leave it up to you to verify in your table, but you should get these two areas that are going to need to be subtracted. Which gives us a probability of 0.8645.